We're moving to Chapter 5 on integrals. So as I've mentioned before, we've been covering the first branch of calculus, differential calculus, involving the derivative, which solved the tangent problem, right? The motivating problem was the tangent problem. And now we're ready to move on to the second branch of calculus, integral calculus. So we'll just be doing the first part of Chapter 5, which will give you an introduction to this branch of calculus, and then you'll pick up where we left off in Calculus 2, and then Calculus 2 will cover the rest of the topics in integral calculus. So in the first section, 5.1, we're going to introduce the area and distance problems. So the area problem is the motivating problem for this branch of calculus, just like the tangent line. The slope of the tangent line was the motivating problem for differential calculus. And then we'll look at the distance problem, which also uses similar concepts as solving the area problem. Here I'll introduce what the area problem is. So the idea is you have a graph of a function. Here this curve is our function f of x. And then we look at an x interval from some number a to some number b. And the question is, what is the area of this region that lies below the curve down to the x-axis that's between a on the left and b on the right? And so you can see this region has a curved top, and that's what makes the problem challenging. We have formulas in geometry that we can use to find the area of regions that have straight edges, like polygons. But this is different because of having that curved top. And so the formulas for geometry don't apply to finding the area here. So what our approach is going to be is to approximate the area by dividing it into polygonal shapes. And we're going to use rectangles because we can easily find the area of rectangles. So the basic idea is we will subdivide this interval between a and b into some number of subintervals. And then at each one of these, we'll make the sides of our new rectangles. And then with each rectangle, we'll have to decide exactly where to put the top, right? We'll discuss that as we get into the details. But basically, you want your rectangles to fit pretty closely with the top of the region. And then you find all the areas of those rectangles and add them up. Now that's only going to be an approximation to the area we're looking for. So we're going to need how to figure out how to move from an approximation to the exact area. And I just wanted to go ahead and mention the approach we're taking to solve this problem uses a similar strategy for the method we used to solve the tangent problem, finding the slope of a tangent line. If you remember when we first devised our strategy there, we started by approximating the slope of the tangent line by using the slope of a secant line. We're doing the same thing here. We're approximating the thing we're looking for, in this case, the area. And then once we had our approximation, we had to figure out how to improve the approximation. So with the secant line, we kept moving the second point closer to the first point, and every time we did that, it made our secant line closer to the tangent, so we were getting a better approximation for the slope of the tangent. And then you just had to repeat that process to infinity. Keep making the approximation better. Keep making the secant line closer to the tangent line. And that is where we needed the concept of a limit. You want to keep improving it into infinity. We need this idea of a limit to continue doing that. So we're going to use that same exact approach here. First, we'll figure out how to approximate the area we're looking for, which we just saw our basic idea for that. Then we'll have to figure out how to improve the approximation, and then apply a limiting process so it continually improves the approximation to infinity. We're going to use this example as a way to sort of develop our strategy by thinking through this example. So here we're just given a region called S, and it's defined by this curve y equals x squared, which you can see part of that curve here, that parabola in blue. And then we're given the x interval from 0 to 1, which are marked, those points are marked off. And then we create our region by sketching below the curve and stopping when we get to the x-axis, and then bounded on the left and the right by the given numbers 0 and 1. And so you can see shaded in blue here, this is the region S that we're trying to find the area of. Okay, so we're going to try some different attempts at creating our rectangles in different, we'll see there are different ways you can create your rectangles. So we'll look at some of the options for how to create the rectangles and then how to calculate the areas of the rectangles and add them up. Before we start subdividing into rectangles, we can make one really rough approximation that we can say that we know this area is greater than 0, that part's obvious, but we can also say it's less than 1, because if you create a box that has height 1, or width 1 and height 1, right, the area of that box would be 1 times 1, which is 1, and that box contains the shaded region S. So definitely the region S has area less than 1. So we have that very rough estimate between 0 and 1, but we want to get a much better approximation than that. So for our first attempt at creating our rectangles, we're going to decide to use 4 rectangles, right? So you have to decide how many you want to use. So we're going to try 4. So we need to subdivide the interval from 0 to 1 into 4 separate sections. Now, they don't have to be equal width, but usually that's the simplest way to approach this, is make all the rectangles have the same width. And so you can easily figure out where those marks would occur, and they're labeled here for the 4 rectangles. So then you create a vertical line at each of those subdivision points. Those are going to be the sides of the rectangle. And then the next question is where to put the top of each rectangle. So, for example, this rectangle we're calling S3, we could put the top sort of midway between the left and the right sides we've drawn, or it could be up at the highest point or down at the lowest point or anywhere in between. So for each of these rectangles we have to first decide where are we going to put the top of each one. There are many different ways you can choose where to put the top of each rectangle, but in this first attempt what we're going to do is choose the height based on the right edge of the strip. So what I mean by that is, let's look at this third rectangle. The subinterval goes from 1/2 to 3/4. So what we want to do is go to the right edge, which is at 3/4, and go up until it hits the curve, and that's where we're going to put the top. And we do the same for all 4 of them, right? So the first interval is 0 to 1/4. The right edge is at 1/4, so we move vertically till it hits the top, or hits the curve. That's where we're going to put the top of that rectangle. So we've done that for all 4 of these. Okay, so then how do we visually see where the top of each rectangle is? But we need to now know the dimensions of each rectangle so that we can find the area of each rectangle. The width of each one is clear, right? Each one of these has width 1/4. Now for the height part. Well, because we use the right endpoint and move vertically till it hit the curve, just think about plotting a point on this curve. If you were to graph f of x, you would take your x value and plug it into the function, and that would give you the y coordinate, which would be the height of that rectangle. Okay, so the function here has formula f of x equals x squared. So this first rectangle, the height would be f evaluated at 1/4. And then plugging into the formula, x squared, plug in 1/4, you get 1/4 squared for the height of this rectangle here. For the second rectangle, it's the same idea. To find the height of this, go to the right endpoint, which is 1/2, plug it into your function. That gives you the y-coordinate here, which is the height of that rectangle. So f evaluated at 1/2 will give you the height of the second rectangle. And then applying that formula, that equals 1/2 squared. For the third rectangle, the right endpoint is at 3/4, so the height is f evaluated at 3/4. And then for the fourth rectangle, the right endpoint is 1. So to get the height, you plug 1 into the function, f of 1, which would be 1 squared. So now we know the dimensions of all 4 rectangles. They all have width 1/4, and then they all have different heights that we just calculated here. So the next step will be to calculate the areas and add them up. Now we're ready to add the areas of the 4 rectangles we just created. The notation here, we're using capital R sub 4. So the capital R stands for right. And the reason why we use that is because, remember, we used the right endpoint of each subinterval to determine the height of these rectangles. The subscript 4 indicates the number of rectangles that we chose to use. Okay, so let's look at the calculation for R4. So again, R4 represents the sum of these 4 rectangles, where the heights are determined by the right endpoints. So notice in the formula here for R4, it's a sum of 4 things. So each one is the area of one of the rectangles. So this first calculation, this is the first rectangle. Call it rectangle 1. And then this one, rectangle 2, and so on. Okay, so let's look at the calculation of rectangle 1. Notice it's 1/4 times 1/4 squared. Now remember where those numbers came from. So 1/4 is the width of that rectangle. 1/4 squared is the height of that rectangle, and we calculated that height on the previous slide. Just as a reminder how we found it, we took the right endpoint of the first subinterval, which is 1/4, plugged it into our f of x to get the y-coordinate here, which is the height of that rectangle. And since the formula for f of x is y equals x squared, we got 1/4 squared for the height. And then it's the same idea for each one. For rectangle 2, 1/4 is the width. This is what we calculated for the height by plugging the right endpoint, which is 1/2, into our function. And then follows that pattern, width times height for the third rectangle, and width times height for the fourth rectangle. So simplifying that, you would get 15/32, right? You'd have to square out, multiply, get a common denominator, add it all together. You get 15/32. Putting that in a calculator, we get this decimal. This is our approximation to the area S that we were given. Now, look at the area we just found. R4 is the sum of all these blue shaded rectangles. The area we're looking for is below this curve. So you can see from the picture the area we found is a little too big because it sticks up above the region we're looking for in some places. So we know that our approximation is too big. So the actual area, which we're calling A, it has to be less than the value we just calculated. So our original estimate, we knew the area was between 0 and 1. Now we've narrowed it down more. We now know it's less than this decimal here, so it's significantly less than 1, right? So we'll continue looking at some other approximations and see if we can improve our estimate even more. Now we're going to start over and make a new approximation using different rectangles. We're still going to use 4 rectangles, but we're going to choose the heights differently. So for each subinterval, we've still got our 4 subintervals. Let's look at the third one. Last time we used the right endpoint and we went up till it hit the curve, and that's where we put the height. This time we're going to use the left endpoint. So for this third rectangle, the left endpoint's at 1/2. We move vertically till it hits the curve. We're going to put the height there. So we do that for all 4 of these. Now notice the left rectangle, its left endpoint is right here at 0, which has 0 height. So that rectangle, we don't even see it because it's basically reduced to nothing with having height 0. But it's still part of our calculation. Okay, so the notation we're going to use here is L4. So the L, you can probably guess, means left, because we're using the left endpoint to determine the height. And the 4, same as before, is the number of rectangles that we're using. Okay, so L4 will be the sum of those 4 rectangles. Okay, so let's go ahead and do the calculation. So we need the width and height of each rectangle. Notice all of them have width 1/4, but the heights are different. Let's look at the third one for an example. To find the height, this time we need to go to the left endpoint, which would be at 1/2. And then to find that height, because it hits the curve, just plug 1/2 into the function y = x squared, which would be 1/2 squared, and that's the height of that third rectangle. So we do the same thing for all 4. So for each one, we have width 1/4 times the height, right? And this is for rectangle 1. And then just follow the same pattern, right? I don't think I need to write it all again. Width times height for rectangle 2. Notice it used 1/4 plugged into our function for the height. For rectangle 2, the left endpoint is 1/4, so that's what we plugged in. Third rectangle, width times height, plus the area of the fourth rectangle, width times height. Simplifying all this gives us the fraction 7/32. Putting in a calculator, we get 0.21875. Now the question next is whether this estimate is too big or too small compared to the actual area we're looking for. So remember, the actual area is below this curve, shading everything below this curve down to the x-axis. You can see the rectangles we sketched here, it's too small, right? They leave all these gaps that are unaccounted for. So the actual area is bigger than what we just found, or our estimate is too small. So here we've expressed this. The area we just found is less than the actual area. This other number is what we found on the previous slide when we used the rectangles determined by the right endpoint. And remember, we determined that area was too big, so the true area is less than our first estimate, but the true area is greater than this new estimate. So just to label this, this number is L4, this number here was R4. So now we've narrowed down the true area even more. All right, originally we knew it was somewhere between 0 and 1. And then on the last slide, we narrowed it down to say it's less than this decimal, 0.46875. But now we can say even more. the true area has to be between these two decimals that we found. So we're going to continue making estimates to try to improve that even more. Now we're going to start over with some new approximations to try to get even a better idea of the true area. And the idea here is we're going to use a larger number of strips, right? The last two estimates we made, we were using 4 strips, which created our 4 rectangles. So in this next attempt, we're going to use 8 strips. And we're going to keep them to have equal width. So our x interval goes from 0 to 1. We're going to divide that into 8 equal sections. So the first subinterval would go from 0 to 1/8. The next one would be 2/8, 3/8, 4, 5, 6, 7, 8/8 all the way. So we've got 8 rectangles. And then the next question is always, where are you going to put the top of each rectangle? So we're going to try it in 2 ways, the same 2 ways we did before. One is where we use the left endpoint of each subinterval. So take, for example, this subinterval here. The left endpoint is right here. We move vertically till it hits the curve. That's where we put the height. And we've done that for all 8 of these rectangles. The second estimate we're going to make, we'll use the right endpoints. So for each subinterval, let's just pick this one here. You go to the right endpoint, move vertically till it hits the curve. That's where we'll put the height. Okay, so we're going to now calculate the areas for both of these cases to get our new estimates. So based on the pictures we just sketched, we can calculate 2 more estimates. One of them we would call L8. That's the version on the left where we use the left endpoints to determine the height of each rectangle, and the 8 indicates we used 8 rectangles total. And so this time the width of each rectangle would be 1/8 instead of 1/4. And then you could calculate the heights in the similar way we did for L4. It's just so there are more rectangles. Each case, use the left endpoint to determine the height by plugging the left endpoint into the function. And then you add up all 8 of those, and for L8 we would get this number here when you put it in decimal form. And then we do a similar process for the picture we had on the right where we use the right endpoint, so we called it R8, 8 rectangles using the right endpoint to determine the height of each one. Find all those areas, add them up, and we get this decimal here for R8. And then again, based on the picture, we can see that R8, the rectangles were taller than the region we're trying to find. So we knew the estimate R8 was too big. So the actual area is less than R8. And we could see from our picture of L8 that that estimate was too small because the rectangles all lie below the curve. So the true area is bigger than L8. So now we've narrowed it down even more. This interval for A is a smaller interval than we found using L4 and R4. So we've got it pretty close, well, fairly close, right? We know A is basically between 0.27 and 0.40, some approximately. So we could stop there and we could say, here's our estimate we're going to present. A is between these two numbers. But we could continue on and try to improve it even more. So what you might notice is when we went from 4 rectangles to 8 rectangles, the interval got more narrowed. In other words, we're zooming in more towards the actual value of A. So it makes sense that if we increase the number of rectangles beyond 8, it will continue to improve our approximation. So if we had a lot of time and commitment to this problem, we could keep finding new approximations and trying to get it better and better. So here are the results if we chose to do all those calculations for several different attempts. So n here in the table represents the number of rectangles. And so here we've tried 10 rectangles, 20, 30, 50, 100, 1,000. And then in each case, we did the left endpoint version and the right endpoint version for determining the heights. So just imagine how much work this was, especially for when you have 1,000 rectangles. You have to find the areas of all 1,000 of them and add them all up. First using left endpoints, then you do it again using right endpoints, right? So you obviously need a computer to help with this process. But look at each case. So if 10 rectangles were used, that should be better than the one we just did where we only had 8. So now we have the area between these two numbers, around 0.28 to 0.38. When we increase to 20 rectangles and we add up our left endpoint version and our right endpoint version, now it's narrowed down even more. It's between 0.31 and 0.36. And then we go to 30, 50, and so on. Notice by the time you get to 1,000, it's really narrowed down quite a bit. Our lower estimate is 0.33, etc. The upper estimate's 0.33, etc. Right? They're very close. So we've really zoned in on the area of A is between these two numbers. So if we wanted to present just one number as our estimate, we could just take this. We know that with 1,000, this is going to be the best out of all the estimates we have. And so we're going to just ignore the others and use that. We're just going to average these two numbers, the left and right endpoints of our interval. When you do that, you get this number here, and that we could present that as our estimate for the area. It's still probably not perfect, right? We could make it better by doing even more than 1,000 rectangles. But here you're starting to see our strategy that I described earlier playing out. We figured out a way to approximate the area we're looking for by using these areas of rectangles. The next step was to figure out how to improve the approximation. And we figured out by increasing the number of rectangles, that improves the approximation. So next is we need to introduce the limiting concept. If we were to continue to increase the number of rectangles forever, that should take us to the exact area. So that's what we're working towards in this section. So we just saw that it seems that as we increase the number of rectangles, our approximation gets better. And we can illustrate that with this figure here. So there's 3 pictures here. The one on the left is R10. So the 10 means there are 10 rectangles. The R means we use the right endpoint to determine the height of each one. To the right of that, we have R30. So this one uses 30 rectangles and also right endpoints. And then R50, this one uses 50 rectangles. Now notice that as we use more rectangles, the overhang reduces. Look how much on R10, there's quite a bit of extra area that's being added in that shouldn't be there. But when we increase to 30 rectangles, that overhang decreases. And when we go up to 50 rectangles, it becomes really hard to even see that there's very much overhang. So this really helps to visualize why our approximations improve when we increase the number of rectangles. On the next slide, we'll look at a similar picture using the L left endpoint, and we'll see the similar thing there. Here's a similar picture where we used the left-hand versions of these rectangles. So the first one is L10, so this one uses 10 rectangles. And then L30 uses 30 rectangles. And then 50 rectangles. So all of these, again, are using left endpoints to determine the height. And we saw in those cases the rectangles lie below the curve in all cases. But notice in the graph on the left, there's quite a bit of white space missing that we didn't account for that's in the true area. But when we increase the number of rectangles, that white space decreases. And by the time you get to 50, you can barely see it, right? So we're seeing the same thing with the left sums compared to the right sums, that the number of rectangles will improve the approximation. So then we introduce the limiting concept. We want to continue to increase the number of rectangles to infinity. And so n is the number of rectangles. So we need to take the limit as n goes to infinity. And so here we've taken the limit of the RNs as n goes to infinity, and we've taken the limit of the LNs as n goes to infinity. Remember the RN and the LN, those are our approximations. They're two different approximations to the area we're looking for. Okay, so Rn and Ln are just approximations, but when we take the limit, that becomes the exact area, right? So the exact area is the limit of our approximate areas. And the limit is as the number of rectangles goes to infinity. I did want to point out, though, that we're really just defining the area to be that. It's not like we found this is the exact answer to the area. It just seems intuitive that this limit process would give us the area we're looking for. So we just define the area to be this limit. Now here we say it equals 1/3. Now where did that come from? If you look back at the previous slide, where we had the or 2 slides back, we had a table where we were using different numbers of rectangles. So the first row had 10 rectangles, and then we kept increasing the number of rectangles. If you look at Ln and Rn as you move down the table, those numbers get closer and closer to 0.33. And so that's 1/3. The fraction has decimal form 0.333333 forever. So we guessed, based on that these approximate areas, Ln and Rn, were approaching 1/3. So we guessed that as the value of the limit. Now we're going to generalize the strategy we just developed in the last example. So here we have some general region defined by this function f of x is the top, and then we're restricting it to an interval from a to b on the x-axis. So the shaded blue region is what we're trying to find the area of. So just like we did in the example, we're going to start by subdividing this interval on the x-axis into n strips. So the number of strips could be any number that we want. And we do that by making equally spaced divisions. So in general, they don't have to be equally spaced, but that's going to make our calculations a little easier if we just do it this way. And we're going to name those positions x1, x2, x3, and so on. And we would finish at xn, right? This last one's not labeled, but where b is, we could call that xn. And so that notation indicates there are n of these subdivisions. And each subinterval will correspond to a rectangle once we fill in the rest of the rectangle. Now we can go ahead and calculate a formula for the width of each of these, and they all have equal width. So the way we're going to calculate it is we'll take the entire length from A to B and divide it by n, and that will give you the width of n equal pieces. So the length of the entire interval from A to B is just the right endpoint minus the left endpoint. So that's the B minus A. And then we divide it by n to get n equal pieces and this would be the width of each one of them. And the name we're going to give to that is delta x. So visually here, delta x is the width of each one of these, and again they're all the same, so they all have width delta x. So now we've established our n strips, and the strip is referring to, like, the first strip is the area below the curve in this first subinterval, so just this region here. Second strip, region below the curve here. Now each strip is now going to be approximated by a rectangle. So in each of these cases, we have to decide where we're going to put the top of each rectangle. So we've seen there are different choices for that, and any of those choices were fine that we experimented with in the first example. In this first attempt, we're going to use the method of using the right endpoint. So if you remember how that worked, let's go to our first subinterval. We go to the right endpoint, which is x1, and we move vertically till we hit the curve, and that's the position where we're going to put the top of that rectangle. And then you go to the second strip, you do the same thing. Go to the right endpoint at x2, move vertically till it hits the curve. That's where we'll put the top. So we've done that all throughout here, and we've got our total of n rectangles here. So now we want to work on finding the area of each one of those rectangles. So what we do is we choose an arbitrary rectangle and do the calculations for it. So this is going to be our arbitrary rectangle. This is the ith rectangle in our list. And notice the the names of the endpoints, right? The first rectangle ends at x1, the second rectangle ends at x2, so the ith rectangle ends at xi. So the strip, we refer here to SI, that's the area of the strip, and remember the strip is not the rectangle, it's the region that's actually below the curve down to the axis, just on this small interval. And we're using this blue rectangle here to approximate the area of the strip SI. So the blue region here we could call R, well maybe we shouldn't call it RI, but it's the area of the ith rectangle. That's what we want to now calculate. So we've already established the width is delta x. The height, we use the right endpoint, which is at xi. We plug it into our function. That means move vertically till you hit the curve. The y-coordinate of that point would be f evaluated at xi. Okay, so for the ith rectangle, the width is what we're calling delta x, and the height is f evaluated at the right endpoint at xi. So the area of that rectangle, we can see over here, is just the product of the width and the height. Okay, so that, by doing it for an arbitrary rectangle, we can apply that same formula to every single rectangle. And that's what we've done here. So this is the sum of n areas corresponding to the n rectangles we see here. So for the first rectangle, the height is f of x1, the width is delta x. So there's the product, height times width. Plus, and then this represents the area of the second rectangle. The width is delta x, the height is f of x2. And then we go all the way down till we get to the nth rectangle. The width is delta x, the height is f of xn. So this formula is what we've been calling R sub n. Remember, R means we use the right endpoint to determine the heights. N represents the number of rectangles, which here is an unknown number. It's arbitrary, and we're just calling it n. These graphs here show what the regions would look like for different choices for n, where n is the number of rectangles. So here, if we chose to use 2 rectangles, we would just have two subdivisions. And so we're using the right endpoint to determine the height. So for this rectangle here, we use the right endpoint. For this rectangle, use the right endpoint. And we would find the area of these two rectangles. And you can see that's not a very good approximation because there's this big gap here, another one here, right? And the rectangle overhangs here. So it doesn't fit very well into the region. If we go to 4 rectangles, we divide our interval into 4 equally spaced subintervals. Use the right endpoint for each one to determine the height. It's a little bit better, but still some pretty big gaps there. If we go to 8 rectangles, you can see it starts to fit the curve better. Here's 12 rectangles, even better. So we saw this idea earlier, right? The more rectangles you use, the better your approximation is going to be because the rectangles are going to fit more closely into the region you're trying to find. Right, the main issue with using more and more rectangles, if you're calculating these by hand, it becomes a lot to calculate. You have to find a lot more areas of all the rectangles. But that's the idea. Increasing the number of rectangles will improve our approximation. So just like we did in example 1, we're going to define the area that we're looking for, which is the area under the curve between A and B, by taking our approximation. So this expression in the brackets, that's the sum of the areas of the n rectangles. It's just an approximation. But when we take the limit of that as n, which is the number of rectangles, goes to infinity, we now define this to be the exact area under the curve. And we saw why that makes sense intuitively. This limiting process should take us from just an approximation to the exact value, exact area. Now, one thing we're assuming in our definition is that the function is continuous. One reason why we assume that is to ensure that this limit exists. Right? If f is continuous, it means you can bring the limit inside, or let's just think of it this way. Limit of a continuous function would always exist in this context. Okay, so then here's a conclusion that's really interesting. Suppose we had used left endpoints to determine the heights of the rectangles instead of right endpoints. And you did the same, you defined it the same way, right? Because we saw the same thing. If you increase the number of rectangles, it doesn't matter how you determine the tops of those rectangles, whether it was right endpoint or left endpoint, the approximation got better when you increase the number of rectangles. So it makes sense to define the area using the left endpoints or the right endpoint method. But we also saw that the L4 was different from R4 and L8 was different from R8. You would get different rectangles when you use left endpoints versus right endpoints. So using the left-handed endpoints, the expression for the area of the n rectangles will be different than it is when we used right endpoints. But what's interesting is when you take the limit of these two expressions will be the same. And that's basically telling us it doesn't matter how you choose the tops of your rectangles. It will if you're just doing a finite sum. The areas you'll get will be different if you say 4 rectangles using right endpoints versus 4 rectangles using left endpoints. But once you take the limit, it doesn't matter how you chose the tops of the rectangles. Now that we saw that for finding the area using our strategy, it doesn't matter if you chose the heights of the rectangles using the right endpoint or the left endpoint of each subinterval, we can now extend that and think of other ways to choose the height that are different from the right or left endpoint. And this is the idea we're introducing here of using a sample point. So what we do is in each subinterval, you choose any point you want between the left and right endpoints. And you call it a name like this. So for the first subinterval, the position we chose is right here, and the name of it is x1 star. And that's called a sample point from the first subinterval. Then we go to the second subinterval, and you choose any point between the left and right endpoints. In this picture, we chose it right here. And then the name of that point will be x2 star. That's the sample point from the second subinterval. We do the same in the third subinterval. Choose any number in there, call it x3 star. Continue doing this for all n of these. So here's the generic one. This is the ith rectangle. The sample point we call xi star. And by the way, the sample point could be the left endpoint or the right endpoint, or any point in between. Okay, so now we have our sample points. So now we can generalize our expression for the area. So in the brackets, we have the sums of the areas of all n rectangles. Now notice how the heights were chosen. It's based on the sample point. So in the first subinterval, here's the sample point. We move vertically till we hit the curve. That's where we're going to put the height of that rectangle. In the second subinterval, we chose our sample point here. We go vertically till we hit the curve. That's where we put the height. So notice the height here is different than if we had chosen the right endpoint or the left endpoint. And we do this all the way down. So the height of the first rectangle would just be f evaluated at x1 star. And the width is still what we call delta x. All of the rectangles have the same width, delta x. So here's that area of the first rectangle, height times width. Plus, go to the second rectangle, we have height times width. Again, it's using the sample point from the second subinterval. And then we go all the way down to the last one, height times width of the nth rectangle. So in the brackets, that's our approximation. That's the areas of the n rectangles all added up. But when we take the limit of that expression as the number of rectangles goes to infinity, then it becomes the exact area below the curve. Okay, so now we've developed the notation we need, right, to start writing general formula to solve our area problem. There are some particular ways that we can choose our sample points that we have special names for, and those are lower sums and upper sums. So by lower sum, what we mean is that in each subinterval, you choose your sample point to make your rectangle's height as small as possible. So notice in this subinterval, if we picked the left endpoint, it would be a very tall rectangle. And if we picked something in between, it brings it a little bit shorter. The shortest rectangle comes from using the right endpoint in this particular case. Now moving to the second interval, the shortest one comes by this point here. So a sample point that's about in the middle of that subinterval. Right, if we had chosen the left endpoint, it would have been a taller rectangle. Continuing on, the third one, this one's shortest by choosing the left endpoint. And if we skip to the last one, it's the shortest rectangle by choosing the right endpoint. Okay, so each subinterval has its own sample point that's different in each case, but it's chosen in such a way to get the shortest rectangles possible. If you choose your sample points that way, we call it a lower sum when you add up all the areas. So you can probably figure out based on that what an upper sum would be. So for each subinterval, you want to choose your sample point to make the rectangle as tall as possible. So in this first subinterval, we would want to choose the sample point at the left endpoint. That's the tallest point on that curve over that subinterval. The second subinterval, we get the same thing whether we use the left endpoint or the right endpoint, but that's the tallest choice we could make. And we do that all the way down. This just shows both of them together. So on the first subinterval, the lower sum used the right endpoint to create this rectangle. The upper sum, we used the left endpoint to get the tallest possible rectangle. And then similar here, this is the smallest rectangle we can get, the shortest one. And then in light blue, that's the tallest rectangle we can get for that subinterval. So it's just showing the comparison of the two. Now we know it won't matter when you take the limit which one you did, lower sum or upper sum. You would mainly, the only place this would make a difference is if you're doing an approximation and you're not taking the limit at all, but you're just estimating the area below the curve using one of these two methods. So this type of expression is going to be very important in solving this area problem. It's a sum of the areas of n rectangles, but it's a little bit long to keep writing this type of expression over and over, so we're introducing here a shorthand notation for this type of sum called sigma notation. So it uses the Greek letter sigma, that's the capital sigma, and what we do is we look for a pattern in the terms that were being added. Notice they all look very similar. They're all f evaluated at x of some subscript multiplied by delta x. So we generalize that pattern here. F of x sub I, because I is the thing that's changing from term to term. And then over on the sigma, at the bottom, we put I, which is referring to this I here. And then we put the starting value, the smallest value for I that's used, which in this case you can see is 1. And then at the top, we put the largest value that's used. So if you go to the end, the largest value that's substituted in for I is n. So this notation, when you see this sigma followed by a formula, it tells you to create a sum, and the first term in your sum uses this number, which in this case is 1, for I, and we call I here the index. So you just copy the formula, but you plug in 1 for I, and you get f of x1 delta x. Then you put plus, the sigma is telling you, sigma is the Greek letter S, which stands for sum, right? So the sigma is telling you to put a plus. Now you increase the index by 1. So now we plug in 2 into this formula. So now we have f of x2 delta x. Then you put another plus, and you increase I again. It would be 3. And we're not showing it here. It's in the dot dot dots. But the next term would be f of x3 delta x. And then you keep doing this until you get to the last term, which is when I is equal to n. So you replace this I with n. You get f of xn delta x, and that's where we stop because this tells us n is the last value we're going to use for I. Okay. So down below here, we have two different expressions for the area that we were trying to find. Notice its limit as n, the number of rectangles, goes to infinity, and then we've got the sigma notation. Notice this matches exactly what we have up here. This sigma notation represents the case where we used the right endpoints. Right, let's look at a number line. The ith rectangle was over the interval from x sub I minus 1 to xi. Right, so this is the ith rectangle. And notice in this expression here, we're plugging in xi to determine the height. So this expression here, right, is the same as this, is the formula for using the right endpoints with n rectangles. Okay, so this is using r sub n, right? R means right endpoints. N means there are n rectangles. Now look at the expression below. The only difference is the subscript on x. It uses I minus 1. So for the ith rectangle, x sub I minus 1 is the left endpoint. And so they've plugged the left endpoint into the function to determine the height. So this expression, this sum here, without the limit, that would be Ln. We have n rectangles and we use the left endpoint to determine the height. Putting the limit in front of it now gives us the exact area. It's no longer an approximation. Okay, so this formula here uses Ln. So either one of these works, and the limit will give you the same value, and that value is the area that we're trying to find. In this example, we're given a curve with the function f of x equals 1 over x plus 1, and we're looking over the x interval from 0 to 2. So let's just go ahead and sketch that before we read the rest of the problem. So if I plot some points, when x is 0, y is 1. So we have the point 0, 1. When x is 1, y is 1/2. When x is 2, y is 1/3. And so it's a curved shape. It's just slightly curving. Whoops. Okay, so that's our f of x. Okay, and we're just looking at 0 to 2. So you could go ahead and sketch sides to it. Okay, down to the x-axis, so this is the area we're trying to find. Now in this example, we're only asked to estimate the area. We're not going to find it exactly. And we're told to use, for our sample points, the midpoints. So not a left or right endpoint, but midpoints. And then in part A, we're going to use 2 subintervals. In part B, 4 subintervals. So let's start in part A. We're using 2 subintervals, so that means n. N represents the number of rectangles, which is the same as the number of subintervals. That's going to be 2. Now we know we're going to need this expression delta x, which is the width of each rectangle. And you can see what it's going to be just by, it's pretty obvious from the picture. If we divide the interval from 0 to 2 into 2 equal parts, each one will have width 1, right? But it's not always so obvious. So let's think about the formula. If you remember our formula, it was, for delta x, it was b minus a over n. So here b is 2, a is 0. So that b minus a, the 2 minus 0, is the total width of the interval from 0 to 2. And here we're using 2 subintervals, so n is 2. And so this, when you simplify 2 over 2, you get 1. And that's exactly what we knew it would be, right? The width of each rectangle is 1. Okay, now let's make a picture, a new picture that we can write more on. So here's our tick marks. This was at 1. We had our curve coming down like this. That's our f of x. Now I'm going to show the tick marks. Okay, so we could call the left endpoint x0, and then we need to go 1 unit to the right because our delta x is 1. And that takes us to our next tick mark, which happens to be the number 1, but we're going to call it x1. And then we go 1 unit, another delta x to the right. That takes us to 2. That's our next subinterval marking, and we call that x2. Okay, so now we're going to create our rectangles by moving vertically upward in at each of those markings. Now to choose the height, we need midpoints. Our sample points are next. Okay, so let's choose, and we're using midpoints, so the first subinterval goes from 0 to 1. The midpoint there would be 0.5. Okay, from there we go up till we hit the curve. That's where the height's going to be. Going to the second subinterval, from 1 to 2, the midpoint right here would be 1.5. From that sample point, we move vertically till we hit the curve. That's where the height is going to be for that rectangle. So that's the picture of what we're looking at. Now let's do the actual calculation. Okay, so the name of our approximate area, we could use capital M to represent midpoint, and subscript 2 to indicate we use two rectangles. So instead of L2 or R2, we're using M2 to indicate midpoint. Now look at the first rectangle. The height will be F evaluated at the sample point, which is 0.5. And the width, for now, let's just put delta x. We'll substitute in the number in a minute. And then plus, now we do the area of the second rectangle. So the height will be F evaluated at the midpoint of the second one is 1.5. That's the height times the width delta x. Now let's substitute in numbers here. So f of 0.5, we need to find our formula for f, which is up here, and plug in 0.5. So it will be 1 over 1.5. Times delta x. Now we found delta x a minute ago. For this problem, it's 1. Plus, go to the second expression, we have f evaluated at 1.5. So in our formula here, it's 1 over, the denominator is 1.5 plus 1, which is 2.5. So it's 1 over 2.5, and then the delta x again is 1. So one way to simplify this, we could think of 1.5 as 3 halves, 3 over 2. So 1 over 1.5 would be the reciprocal of 3 over 2, which is 2 over 3. And we don't need to write the multiplied by 1. Plus, the 2.5 is 5 over 2, right? It's 5 halves. And that means it's in the denominator there, so the reciprocal of 5 halves is 2/5. And then we could get a common denominator of 15. So the 2/3 becomes 10 over 15, right? Multiplied by 5 over 5. Plus, next one multiplied by 3 over 3, we get 6 over 15. And then adding together, we get 16 over 15. So just slightly bigger than 1. That's our approximation for A, right? So A is approximately 16 over 15, although that's probably not the best approximation because we only use 2 rectangles, right? You should really use a larger number of rectangles to get a good approximation. So in part B, we're going to go up to 4 rectangles and redo the calculations, and we should get a closer approximation when we do that. Now for part B, we were asked to use 4 rectangles, and we're still going to use midpoints to determine the heights. So we want to take our x interval from 0 to 2 and divide it into 4 equal pieces. So again, it's pretty clear where those subdivisions are going to be. You'll have one at 0.5, 1, 1.5, and then the last at 2. But if it weren't obvious, we would always use our formula for delta x. So delta x, as we know, the formula is b minus a over n. So in the numerator, that's 2 minus 0, and this time n is 4, and that simplifies to 1/2. So the width of each subinterval should be 1/2. So then we could start marking them off. The first one starts at 0, so you go 1/2 unit to the right. That puts us at 1/2 or 0.5. That's our first subdivision. Then we go 0.5 steps to the right from there. That takes us to 1. And then another 0.5 takes us to 1.5. And then the last step of 0.5 takes us to 2. And you can see that creates those 4 subintervals. If we were to give those the standard names, it would be starting with x0, x1, and then the last one is x4. Now we can start sketching in our rectangles so that we know the sides are coming up at those subdivisions. And then for determining the height, we need to label midpoints. So the first subinterval goes from 0 to 0.5. So halfway between there would be at 0.25. And then the next one, halfway between 0.5 and 1, is 0.75. The next one would be 1.25. And then finally 1.75. And then to sketch the rectangles, from each of those midpoints, we move up vertically till it hits the curve. That's where the top would go. Okay, do the same thing with the next one. All the way down. Okay, so that's the picture of what we're going to be calculating the area of. So now for our area, we would call this M for midpoint, subscript 4 because there are 4 rectangles. And then we start our calculations. So the first rectangle, the height would be F evaluated at the midpoint, which is 0.25, times delta x. Plus, we go to the second rectangle, the height is F evaluated at 0.75, width delta x. Plus, on the third one, F evaluated at 1.25 times the width delta x. And then the last one, F evaluated at 1.75 times the width delta x. So in the next step, we can evaluate the function at those given inputs. So f of 0.25 would be 1 over, and then we have 0.25 plus 1, right? We're plugging into this formula here. So the denominator is 1.25. And then the delta x this time is 1/2. Plus, when we plug 0.75 in, we get 1 over. The denominator will be 1.75. Delta x is 1/2. On the third one, f of 1.25, the denominator will now be 2.25 times 1/2. And then the last one, we plug in 1.75, so the denominator will be 2.75 times 1/2. So then we want to simplify this. And one thing that could help is to factor out the 1/2 that's in every one of these terms. Okay, so in the first term, I'm going to so we have 1 over 1.25, but let's rewrite that. 1.25 is 5/4, and this is the reciprocal of that, so that's 4/5. Now the 1.75, that's 7/4, and we have the reciprocal of that, so 4/7, and we factored out the 1/2. The next one, 2.25, is 9/4. We have the reciprocal of that, 4/9. And then the 2.75 is 11/4. We have the reciprocal of that, so 4 over 11. Okay, and then inside the brackets, if we want to keep this exact, we would need to get a common denominator. And at the same time, it might help if we factor out the 4 that's in the numerator. So pull out that 4. Okay. Now in the brackets, we have 1/5, but our common denominator here is going to just be the product of all 4 denominators, it looks like. So 5 times 7 times 9 times 11. Now that first fraction is, we've pulled out the 4, so it's 1 in the 1/5. So we have to multiply top and bottom by 7 times 9 times 11, right? So 7 times 9 times 11 plus, on the second fraction, we've pulled out the 4, so we've got 1/7. So to get the common denominator, we need to multiply by 5 times 9 times 11. On the third one, the 4 is pulled out. To get the common denominator, we multiply 5, 7, 11. And then the last one, multiply by 5, 7, 9. Okay, so then let's continue up here. So in front we have 1/2 times 4, which is 2. And then inside the brackets, the numerator comes out to 1888. And the denominator 3465. And then multiplying by 2 makes the numerator 3776 with the same denominator. And that fraction may or may not simplify, but I'll just leave it like this. And then to get a decimal for that, putting that in the calculator, this is approximately 1.09. So that last calculation turned out to be kind of messy, but that's not the main point of the problem. Our estimate for the area below the curve is 1.09. Now let's see if that seems reasonable. If we just made one big box here, it would be 2 for the width and 1 for the height, so the area would be 2. And you can see the area we're looking for is definitely less than 2, and the number we found is obviously less than 2, so at least it seems somewhat reasonable. And we know that the answer we got here in part B for our approximation is most likely more close to the true area than what we found in A, because we only used 2 rectangles in part A. So let's summarize what we covered today. We started section 5.1 on the area and distance problems. So far we've just discussed the area problem. We'll get to the distance problem next time. So we developed a strategy for our area problem for how to solve it. And the area problem means finding the area of a region below a graph of a function down to the x-axis between or over a given x interval. So the basic strategy starts by subdividing the x interval and then using those subdivisions to create rectangles that fit close inside the region. To determine the height of each rectangle, we saw we could use the idea of sample points. Once we establish our rectangles, we find the areas of all of them and then add those together. And that gives us the approximate area under the curve. To get the exact area under the curve, we take the limit of our approximations as the number of rectangles goes to infinity.